Chapter 21 of Young and Freedman's University Physics begins a whole new section on electromagnetism. In fact, you can actually buy this large physics textbook in multiple volumes, and this is where the second volume begins with electromagnetism. So chapter 21 is titled Electric Charge and Electric Field, and the first section of this chapter introduces the concept of electric charge. Electromagnetic interactions, they're one of the four basic kinds of forces that are known in physics. These four forces were introduced at the very end of one of the chapters early on in the book. I think chapters 5 or 6 or 7, somewhere in there, the end of the chapter introduces the four basic forces. Of course, the gravitational force is something you encounter in the first part of the book on mechanics. The book will talk later about the strong and weak nuclear forces. We might mention the strong nuclear force a little bit later in this video. The basic idea of electric charge has been known for thousands of years. The Greeks knew that when they rubbed wool on amber, that the amber took on a kind of a characteristic that it could attract and repel various things. And today, if you were to rub fur on a plastic rod, then the fur and the plastic rod will come to have a kind of attraction for each other. Similarly, if you rub silk on glass, the silk and the glass will come to have a characteristic that they come to attract each other. We call this characteristic electric charge. And similarly, even though the plastic and the fur will attract each other, if you take two plastic rods that you've done that to, normally the plastic rods don't do anything. But if you rub fur on two plastic rods, then the two plastic rods will push away from each other. Similarly, if you rub silk on two glass rods, the two glass rods will want to push away from each other. This is because of what we call electric charge. They've taken on a charge. Electric charge is what we say that the plastic, the fur, the glass, and the silk has required, and some of them we say some of them take on a positive charge, and some of them we say take on a negative charge. We wouldn't have to call it that. I think maybe Benjamin Franklin came up with that way of referring to it, but and stuck. And so we say that the plastic took on a negative charge, and the fur took on a positive charge, that the glass took on a positive charge, and that the silk took on a negative charge. That's what we say. Now, aside from the gravitational forces that keep us from flying off into space, most of the forces we experience every day are the result of electric interactions. So what are called the normal forces that push back up on our feet as our feet push down gravitationally, that's the result of the electric interactions of atoms and so forth. Here's some basic rules. As we said, like charges repel, opposite charges attract. Now, they don't have to be the exact like or the exact opposite charges. It's just that the signs themselves, something that is positive in sign will attract something that's negative in sign, and something that is negative in sign will attract something that's positive in sign. They don't have to be the exact magnitude for that to work. Another rule that you learn in this first section is that the total charges in any closed system is constant. So the silk and the glass can exchange some charge, but the total charge will stay the same in a closed system. Another thing that you find out in this section is that the magnitude of a charge is going to be some multiple of the basic charge of an electron or proton. That is to say that the charge of an electron or the charge of a proton seems to be the most fundamental, irreducible amount of charge that exists in nature. Now, you do find out as you go into physics that for example, protons and neutrons are made up of something called quarks, and scientists do talk about quarks having a plus or minus 1/3 charge or a plus or minus 2/3 charge, and so that might seem to contradict this idea. But physicists currently believe that quarks can't exist in a separate form. That is to say, that they're always going to be combined in such a way that the combined charge of the quarks will add up to one of these basic units of the charge of an electron or the charge of a proton. So those are the three basic rules of this section that you find out. Now, I don't know whether you need a review of atoms. Usually somebody who would be this far along in a physics textbook would have already encountered something about atoms, but just to review, these are the things that are in this section on atoms. Atoms are the fundamental building blocks of stuff that we can still identify as distinct stuff. So you can, get electrons out of an atom and protons, but those are all the same. All the electrons and all the atoms in all the world are the same. All the protons and all the atoms in all the world are the same. All the neutrons and all the atoms in all the world are the same. And so the stuff, once you get below the atom, isn't distinct. But if you take all the stuff in the world apart, you get down to these basic atoms, these basic building blocks. Copper, if you take a copper atom apart, if you could, to the electrons, the protons, the neutrons, you don't have distinct stuff anymore. A copper atom is basic copper, and you can't break it down any further and it still be a distinct thing, if that makes any sense. Most people kind of catch on to what we're saying. It's kind of hard to explain, though, really, what you mean by a fundamental building block of this sort. Atoms, as we said, are made up of three basic particles: electrons, protons, and neutrons. Atoms are made up of a very small nucleus surrounded by lots and lots of space, where the electrons are in what we call them shells and orbitals around the nucleus. The nucleus is like the comparison that Young and Freedman give is that a nucleus is like a tennis ball in a area that's several kilometers large. So you can see that the nucleus is very, very small compared to the total amount of space that an atom occupies. Of course, electrons are much, much, much smaller than protons and neutrons are. So, for example, the mass of a proton is about 2,000 times as big as the mass of an electron, and the size of an electron is significantly smaller than the size of a proton. Other important things in this chapter, in this section, the number of protons is what tells you what kind of atom it is. We call the number of protons in an atom the atomic number. Now, normally, there is the same number of protons and electrons in an atom. When an atom is neutral, when it has no charge, in its default, maybe that's not the way to say it, but in its normal state, an atom has the same number of protons and electrons. But I think it's safer to say that the atomic number is the number of protons, because atoms can gain and lose electrons. So an atom can lose some electrons and therefore take on a positive charge, or an atom can gain electrons and take on a negative charge. We call an atom that has taken on such a charge by gaining or losing electrons, we call it an ion. A positive ion is an atom that has lost electrons, and a negative ion is an atom that has gained electrons. And the process of this becoming an ion is called ionization. Well, that's a whole lot of information in this first section of chapter 21, but it gets a lot of stuff on the table so that we can then begin to learn more about electric charge. This chapter is about electrostatics, that is, charges at rest. Later on in the book, of course, we'll get into electrodynamics, where charges are in motion.